In the summer of 1950, four physicists were walking to lunch at a laboratory in New Mexico. They had been talking about a cartoon in a magazine and about reports of unidentified objects in the sky, and the conversation had drifted on to other things by the time they sat down. Then one of them, apparently out of nowhere, looked up in the middle of the meal and asked a question that people have been trying to answer ever since. Where is everybody? He was not making a joke. In the space of a few minutes over lunch, he had worked through the arithmetic in his head, and the arithmetic did not agree with the world outside the window. Our galaxy contains hundreds of billions of stars. Many are billions of years older than our sun. We now know that planets are not rare. Almost every star has them, and a great many are the right size, at the right distance, made of the right materials. If even a tiny fraction of those worlds produced life, and a tiny fraction of that life became curious, and a tiny fraction of the curious ones built ships or transmitters, then the galaxy should be crowded. There should be signals. There should be traces. Somebody should have arrived a long time ago, and instead there is nothing. No signal in 70 years of listening, no structures, no visitors, no evidence of any kind. Tonight, we sit with that silence, not to solve it because nobody has, but because the possible answers say something quietly remarkable about our own situation. If you find yourself drawn to the great open questions of the cosmos, consider subscribing to the channel. Let one of the deepest of them carry your mind somewhere restful as we drift together through the dark. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We rise away from Earth and out of the plane of the galaxy until the whole spiral turns slowly beneath us. 400 billion stars wound into arms 100,000 light years across. Look at it and try to hold the numbers honestly. If you counted one star every second without pausing to sleep or eat, you would need more than 12,000 years to finish. Around most of those stars, planets are turning. Rocky ones, gas giants, frozen ones, scorched ones. Current estimates suggest there are more planets in this galaxy than stars, and that billions of them are roughly Earth-sized and in the right temperature range for liquid water. And every one of them, as far as we can tell, is quiet. Tonight, we will work through why that is strange. We will do the arithmetic that startled a physicist over lunch and see how long it should take a curious species to cross a galaxy. We will look at how much of the sky we have actually searched and discover that the honest answer is embarrassing. We will consider whether the silence means nobody is there, or that something happens to civilizations, or that everyone else has simply decided not to speak. And we will finish somewhere unexpected, because the Fermi paradox is not really a question about aliens. Settle in. Let your breathing slow. Tonight is a night for wondering, not for answers. Let us begin with the arithmetic that started it. Our galaxy is roughly 13.5 billion years old. Our sun is 4.5 billion. That means the galaxy spent 9 billion years making stars and planets before we existed, and a great many of those systems are older than ours by margins we struggle to imagine. Consider what a billion years means. Not 1,000, not 1,000,000, 1 billion. If a civilization anywhere in this galaxy had emerged just 1% earlier than us, 130 million years ahead, they would have had that entire span to develop while our ancestors were still small nocturnal creatures avoiding dinosaurs. And here's the part that made Fermi sit up. Crossing the galaxy is slow, but it is not impossibly slow. Suppose a civilization sends out ships at a modest fraction of light speed, say 1%, which requires no exotic physics. A journey to a neighboring star takes a few hundred years. Unpleasant, but not impossible. Craft. Now suppose that when a ship arrives, it builds a few more ships from local material, and is exponential. Each wave doubles. And when you run the numbers, the wave sweeps across the entire galaxy in something between 5 million and 50 million years. Compare that with the 9 billion years available before we appeared. The galaxy could have been settled entirely hundreds of times over before Earth had oxygen in its air. Even at walking pace on a cosmic clock, there has been an enormous amount of time. So, where is everybody? Now, let's go deeper into the first serious attempt to organize the question. In 1961, a small group of scientists met at a radio observatory in West Virginia to discuss whether searching for signals was worthwhile. The organizer wanted a way to structure the conversation, so he wrote an equation on the blackboard. It has been famous ever since, and it is almost always misunderstood. The equation multiplies together a chain of factors. How many stars form each year? What fraction have planets? How many of those planets could support life? On what fraction does life actually appear? On what fraction of those does intelligence develop? How many of those intelligences build something detectable? And finally, how long such civilizations last? Multiply all of that together, and you get an estimate of how many detectable civilizations exist in the galaxy right now. Here is the crucial point. The equation was never intended to produce an answer. It was designed to break one impossible question into 7 smaller ones, so that a room full of scientists could argue about them separately. And it works beautifully, because it shows exactly where our ignorance lives. The first 3 factors are now measured reasonably well. We know how fast stars form. We know planets are common. We have decent estimates for how many sit at habitable distances. The last 4 are almost entirely unknown. We have exactly 1 example of life beginning, 1 example of intelligence, 1 example of technology, and 0 examples of how long a technological civilization survives. You can plug in optimistic numbers and get millions of civilizations. You can plug in pessimistic ones and get a fraction of one. Both are defensible. That is not a failure of the equation. That is an honest picture of what we do not know. But what happens when the measured parts get better? This is where the story turns uncomfortable. When the equation was written, nobody knew whether planets around other stars were common or vanishingly rare. It was genuinely possible that our solar system was a freak accident, and that most stars had nothing around them at all. That question is now settled. The first confirmed planet around a sun-like star was found in 1995. Since then, we have confirmed thousands using dedicated space telescopes that watch for the tiny dip in brightness as a planet crosses in front of its star. The statistics are striking. Planets are not rare. They are the norm. On average, every star in the galaxy has at least one, and many have several. That implies hundreds of billions of planets in our galaxy alone. A significant fraction of them are roughly Earth-sized and orbit at distances where liquid water could exist. Estimates vary considerably, but even conservative numbers give billions of candidate worlds. And notice what that does to the paradox. Every discovery has pushed the early terms of the equation upward. There are more places for life than anyone dared assume. The raw materials are everywhere. Organic molecules turn up in comets, in interstellar clouds, in the atmospheres of distant worlds. If the paradox had been resolved by finding that planets were rare, we could have relaxed. Instead, the opposite happened. The universe turned out to be far better supplied with real estate than we expected, and it is still completely silent. Every year of exoplanet discovery has made Fermi's question harder to answer, not easier. And yet, there's more to this story. So let us ask how hard we have actually looked. The modern search began in 1960, when an astronomer pointed a radio dish at two nearby sun-like stars and listened for a few weeks. He found nothing, but the project established that the search was at least possible. Since then, decades of surveys have scanned tens of thousands of stars across a range of radio frequencies. More recent programs have expanded the effort enormously, using large dishes to survey 1 million nearby stars and 100 nearby galaxies. Nothing has been confirmed, not once. But before drawing conclusions, we should be honest about the scale of the search, and there is a comparison that puts it painfully into perspective. Researchers once calculated the total volume of search space involved. Every direction on the sky, every possible frequency, every possible signal strength, every moment in time when a transmission might arrive. Then they worked out how much of that total we had actually examined. The answer was roughly equivalent to scooping a hot tub of water out of all the oceans on Earth, examining it carefully, finding no fish, and concluding that the sea is empty. That is where we stand. The search has been real, careful, and thorough within its limits. Those limits are extremely narrow. The Great Silence may turn out to be a genuine discovery about the universe, or it may simply be that we have barely started. Now, let's go deeper into a question the searchers had to answer first. Where in the radio spectrum should anyone listen? The spectrum is vast. Choosing a frequency at random would be hopeless. So in 1959, two physicists published an argument that has shaped the search ever since. They reasoned that any civilization doing astronomy would know about hydrogen, because it is the most abundant substance in the universe, and hydrogen produces a specific natural emission at a wavelength of about 21 centimeters that radio astronomers everywhere would inevitably discover early. It is a universal landmark, not a human convention, but a fact of physics that any observer would find. There is a second landmark nearby, produced by a simple molecule made of oxygen and hydrogen. And between those two frequencies lies a relatively quiet stretch of the spectrum, where the natural background hiss of the galaxy is low and signals stand out cleanly. Astronomers notice something poetic about that band. Hydrogen on one side, hydroxyl on the other. Put them together and you get water. They named the region the water hole, after the places on a savanna where different species gather peacefully to drink. Most searching has concentrated there ever since, but it rests on an assumption worth naming. We are guessing that an alien civilization would reason as we do, value the same landmarks, and choose radio at all. They may use tightly focused lasers. They may use something we have not conceived of. We are searching the one place we would think to look. The journey continues to the one moment that made everybody sit up. On the 15th of August, 1977, a radio telescope in Ohio was performing an automated survey. The output was printed on paper in long columns, with each character representing signal strength during a short interval. Most of the page was zeros and ones, background noise. A few days later, a volunteer reviewing the printout found a sequence that did not belong. The intensity rose, peaked, and fell over about 72 seconds, exactly matching the profile you would expect from a fixed point in the sky, drifting through the telescope's field of view. It was strong. It was narrow in frequency, in a band that natural sources do not usually produce, and close to a frequency that had been suggested as a natural channel for interstellar communication. He circled it on the printout and wrote a single word in the margin. Wow! The name stuck, and it has been argued about ever since. Astronomers have returned to that patch of sky many times over the decades with better equipment. It has never repeated, not once. Various natural explanations have been proposed, including a passing comet, though that suggestion has been strongly challenged. No explanation has been generally accepted. So we are left with 72 seconds of signal from 1977 and nothing else. A single anomaly that cannot be confirmed and cannot be dismissed, sitting in the record like a question that will not close. Now, let's go deeper into an assumption that deserves examination. Are we even loud? There is a common idea that Earth has been broadcasting its presence for a century, and that our old television signals are spreading outward in an expanding bubble, waiting to be picked up. The reality is far less dramatic. Radio signals weaken with a square of distance. A transmitter that fills a country with a clear picture becomes, at interstellar distances, indistinguishable from noise. Our ordinary broadcasts would be undetectable to a receiver like ours from more than a few light years away, and probably less. There are exceptions. Powerful radar systems, particularly those used for missile warning and for mapping objects in the solar system, produce narrow, intense beams that would be detectable much further out. But they point in specific directions and sweep past quickly. And here's the twist that many people find surprising. Earth is getting quieter. Broadcast towers that spray energy in all directions are being replaced by cables, fiber, and tightly focused satellite links that aim their power precisely where it is needed. Efficient communication means less waste, and waste is exactly what an eavesdropper would detect. Our loudest period as a radio source may already be behind us, and it lasted only a few decades. which suggests something important about the search. If other civilizations follow the same path, their detectable window would also be brief. We might be listening for a phase that most technological species pass through quickly on the way to becoming quiet. And yet, there's more to this story, because there is a problem of timing that quietly dominates everything else. Detection requires overlap. Two civilizations must not only exist, they must exist at the same time, in the right relationship, accounting for how long light takes to travel between them. Now consider the proportions involved. Earth has been here for 4.5 billion years. It has had complex life for about 600 million. It has had our species for a few 100,000. And it has had radio for roughly a century. That final number, set against the age of the planet, is about 0.02%. If an alien astronomer had pointed a telescope at Earth and listened for 1,000 years, they would almost certainly have heard nothing, because they would have arrived during one of the 4.5 billion years in which we were not transmitting. They could have listened during the age of dinosaurs, during the long era of nothing but microbes. During the ice ages, every one of those visits would have been a silent one. This is why the final term, the Drake equation, matters more than all the others combined. Not how many civilizations arise, but how long each one remains detectable. If technological civilizations typically stay visible for 10,000 years, then at any given moment, only a vanishing fraction of the worlds that ever hosted one are producing a signal. The galaxy could have hosted millions across its history and still be silent tonight. The signals may not be missing. They may simply be scattered across time rather than space, most of them arriving long before anyone here was listening. But what happens if we look for something other than signals? A signal requires intent. Someone must choose to transmit at the right time, in our direction. That is a great deal to ask. So astronomers also search for technosignatures, unintentional evidence of technology, which requires no cooperation at all. The most famous idea involves energy. A civilization that keeps growing will need more power, and the largest available source in any system is its star. In principle, a sufficiently ambitious species could surround its star with collectors to capture a substantial fraction of its output. Such a structure would have a distinctive signature. The visible light would be reduced or absent, but the energy would still have to go somewhere, and it would emerge as waste heat in the infrared. So astronomers have searched for stars and even entire galaxies that shine too brightly in infrared for the light they emit. One survey examined 100,000 galaxies looking for exactly that imbalance. Nothing convincing was found. Other approaches are more subtle. Future telescopes may be able to detect industrial chemicals in the atmospheres of distant planets, compounds that have no natural source and would only exist if something manufactured them. There have been intriguing individual cases. One star showed strange, irregular dimming that briefly prompted speculation about enormous structures before further study pointed toward clouds of dust. So far has turned out to be nature doing something we had not anticipated. which is itself a kind of result. Possibility we tend to skip over. What if something has already come here? Not visitors in the popular sense, something far more practical. In 1960, an astronomer pointed out that transmitting across light years is an extraordinarily inefficient way to make contact. The energy required is enormous, the delay is centuries, and you must guess where to aim. A far cheaper strategy would be to send small autonomous probes to promising star systems and let them wait. A probe can be patient. It can sit quietly for 1,000,000 years monitoring and only announce itself if something interesting develops. If that is how contact works, then searching the sky is the wrong approach entirely. The evidence would be here, in our own solar system, and we have barely looked. We have mapped Earth thoroughly and the Moon reasonably well, but the rest is enormous. There are millions of asteroids, most of them never imaged closely. There are stable gravitational parking spots where an object could sit undisturbed for the entire history of the solar system. There are the outer moons, the Kuiper belt, and vast volumes of space that no instrument has ever examined in detail. An object a few meters across, sitting quietly in any of those places, would be entirely undetectable with current surveys. We were reminded recently that things do arrive from outside. In 2017, astronomers tracked the first confirmed object passing through our solar system from interstellar space, and a second was found 2 years later. Both appear to be natural, but their discovery established something useful. Material from other star systems passes through here regularly, and we only started noticing it very recently. And yet, there's more to this story, so let us confront the most influential explanation. In the 1990s, an economist proposed a simple and rather chilling framework. Consider the full path from lifeless chemistry to a galaxy-spanning civilization. Simple molecules must become self-replicating. Simple cells must become complex ones. Complex cells must form organisms. Organisms must develop intelligence. Intelligence must build technology. Technology must survive long enough to spread. That is a long chain, and the silence tells us that almost nothing completes it. So somewhere along that path, there must be a step that is extraordinarily difficult, a barrier that nearly everything fails to cross. He called it the Great Filter. The framework itself is not frightening. What is frightening is the follow-up question. Is the filter behind us or ahead of us? If it is behind us, then we have already passed the hard part. Some step in our history was a fluke so improbable that it almost never happens elsewhere. In that case, the galaxy is empty, because getting this far is nearly impossible. And we are extraordinarily lucky. If the filter is ahead of us, the situation is different. It would mean that reaching our current stage is relatively common, and that something reliably stops civilizations afterward. Everyone who came before us hit that wall. The unsettling implication, astronaut, is that these two scenarios look identical from where we stand. The silence is the same either way. The journey continues to what a filter behind us might look like. There are several genuine candidates, and they are more persuasive than people expect. Start with the beginning of life itself. We know it happened here, and we know it happened early, within a few 100 million years of the Earth becoming habitable. That speed is often taken as evidence that life starts easily. But there is a catch in that reasoning. We could only ever observe a planet where life did begin, so the fact that it happened here tells us less than it seems. One data point cannot distinguish between easy and astronomically unlikely. And every living thing on Earth appears to descend from a single origin. The same genetic code, the same chemistry, the same basic machinery. If life were easy, we might expect it to have started several times over, leaving separate lineages behind. We see no sign of that. Then consider the second candidate, which is stranger. For roughly 2 billion years, life on Earth consisted entirely of simple cells. Then, apparently once, one cell ended up inside another, and the two became a single organism. That merger produced the complex cell, which is the basis of every plant, animal, and fungus that has ever lived. 2 billion years of waiting, and as far as we can tell, it happened exactly once in 4 billion years of life on this planet. If that step is as improbable as it appears, then countless worlds may be covered in simple microbial life that will never become anything more. Oceans full of biology and no one to notice. Now, let's go deeper into a related idea about how fragile our situation might be. Some researchers argue that the problem is not any single step, but the sheer number of conditions that must hold simultaneously for a world to remain habitable for billions of years. Earth has an unusually large moon, produced by an early collision, which stabilizes the tilt of our axis and keeps the climate from swinging wildly over long periods. It has plate tectonics, which continuously recycle carbon between the atmosphere and the rocks, acting as a thermostat that has kept temperatures in a livable range for a very long time. It has a molten iron core generating a magnetic field which deflects charged particles that would otherwise strip the atmosphere away, as appears to have happened on Mars. It sits in a fairly quiet part of the galaxy, away from the crowded center where radiation and passing stars would disrupt planetary systems more often. And it has large outer planets whose gravity has influenced the flow of comets and asteroids through the inner system, though whether that has helped or hurt is still debated. The argument is that simple life may be widespread, while the long, stable conditions needed for complex life are extremely rare. Not everyone accepts it. Critics point out that we are reasoning from a single example, and that we may be mistaking the particular circumstances of our own history for requirements. There may be many paths to a stable world that we have not imagined, but the possibility remains open. Microbes may be everywhere, and anything more than microbes may be almost nowhere. But what happens if the filter is not behind us? This is the possibility that people find genuinely uncomfortable, so it is worth handling carefully and calmly. If the difficult steps are all behind us, then technological civilizations should be common, and the galaxy should show evidence of them. It does not. So, one alternative is that civilizations reliably fail after reaching roughly our stage. A species that becomes technological, acquires the ability to alter its own environment on a planetary scale, and to build things it cannot fully control, to manage them. There is a related argument that is more subtle. The technologies that let a civilization spread across a galaxy are the same technologies that let it destroy itself. And destruction is always faster and easier than expansion. However, it is worth being clear about how weak this reasoning actually is. For a filter ahead to explain the silence, it would have to work on essentially every civilization everywhere without exception. Not most of them. All of them, across enormously different biologies, histories, and circumstances over billions of years. Universal failure is a very strong claim, and nothing in our experience supports it. A filter that catches 99% of civilizations still leaves plenty of survivors to fill a galaxy. So while the possibility cannot be dismissed, it requires something far more absolute than any specific danger we can currently name. And yet, there's more to this story, because there is a completely different family of answers. Perhaps they are there, and simply not speaking. The gentlest version proposes that advanced civilizations are aware of us and have chosen not to interfere. The reasoning is that a young species learns more and develops more authentically if left alone. Contact would overwhelm rather than help. It is an appealing idea, and it has an obvious weakness. It requires universal agreement. Every civilization everywhere adhering to the same policy for millions of years with no defectors, no accidents, and no leaks. Any one exception would end it. The darker version comes from game theory, and it was made famous by a novelist. The argument runs like this. You detect another civilization, but you cannot know its intentions, and you cannot know how fast it will develop. It might be harmless now and dangerous in a few centuries. It cannot know your intentions either, and it knows that you know that. That chain of suspicion, combined with the impossibility of verification across light years, might make silence the only rational policy. And it might make the safest response to any detection an unpleasant one. In that picture, the galaxy is not empty. It is full of civilizations that have each independently concluded that being noticed is dangerous, all listening carefully and none transmitting. It makes for extraordinary fiction. As science, it is difficult to test, which is the fundamental problem with all of these explanations. Now, let's go deeper into two possibilities that are less discussed and, to my mind, more interesting. The first suggests we are looking in the wrong direction entirely. We assume that an advanced civilization expands outward because that is what growing populations have always done here. But expansion across light years is extraordinarily slow, expensive, and offers almost nothing in return. A colony 20 light years away cannot be governed, cannot trade usefully, and will diverge into something unrecognizable within a few generations. Meanwhile, technology has been moving in a different direction. Faster, denser, smaller. More computation in less space, using less energy. If that trend continues, a mature civilization might find that everything it wants exists inward rather than outward. Vast simulated environments, thought running at speeds we cannot imagine, in a physical footprint smaller than a planet. Such a civilization would be almost undetectable, not hiding, simply uninterested in the empty space we keep searching. The second possibility inverts the whole question. We assume we are late, arriving after billions of years in which others could have appeared. But small red dwarf stars, which vastly outnumber stars like the Sun, burn steadily for trillions of years. The universe is not old. It is barely getting started. By some calculations, the overwhelming majority of all life that will ever exist has not appeared yet, in which case the silence has a simple explanation. There is nobody to hear from yet. We are not alone because everyone died. We are alone because we are early. But what happens when we consider transmitting deliberately? This has become a real argument among scientists, and it is not merely theoretical. A handful of deliberate messages have already been sent. In 1974, a large radio telescope transmitted a short-coded picture toward a distant star cluster, a demonstration more than a serious attempt, since it will take 25,000 years to arrive. Since then, several groups have proposed more systematic broadcasting. The reasoning is straightforward. If every civilization decides that listening is safer than speaking, then everyone listens and nobody transmits, and the silence explains itself. Others argue strongly against it. Their position is that we have no idea what is out there, that any response would arrive centuries after the decision was made, and that no small group has the standing to speak on behalf of an entire planet. There is also a middle position worth noting. Some argue the debate is largely symbolic because a civilization capable of reaching us would detect Earth's biosphere directly. The oxygen in our atmosphere has been broadcasting the presence of life here for 2 billion years, far more loudly than any transmitter. That is a sobering thought. If being noticed were genuinely dangerous, the danger began long before us, and nothing we choose now would change it. The debate continues without resolution and without any agreed mechanism for deciding. And yet, there's more to this story, and it is the most hopeful part. We may be close to answering at least one piece of this, and much sooner than most people realize. The question of whether life is common has always been the hardest term in the equation, but it is now becoming an observational problem rather than a philosophical one. When a planet passes in front of its star, a small amount of starlight filters through its atmosphere on the way to us. Different gases absorb different wavelengths, so that filtered light carries a chemical fingerprint of the air. We can now read those fingerprints. The current generation of space telescopes has already measured carbon dioxide, water, and other molecules in the atmospheres of planets many light years away. What we are looking for is a combination that should not persist. Oxygen alongside methane, for instance. Those two react with each other and should not coexist for long. Finding both together would mean something is continuously replenishing them. On Earth, that something is life. There are complications. Some non-biological processes can mimic these signatures, and disentangling them will take years of careful work. Nobody expects a single decisive observation. But within a few decades, we may have surveyed enough atmospheres to know whether biology is common or rare. And that single number would transform the paradox entirely because it would tell us which half of the filter we are dealing with. Take a quiet moment to reflect on what this means, astronaut. Here is the thing about the Fermi paradox that took me a long time to appreciate. It is not really a question about aliens. Every serious answer to it is a statement about us. If the hard step is behind us, then what happened on this planet was extraordinary, and we are holding something the galaxy has almost never produced. If the hard step is ahead, then the question becomes, what kind of civilization survives its own capabilities? If everyone is listening and nobody speaks, that says something about how caution behaves at scale. If we are early, then the story of intelligence in this universe has barely begun, and we are near the opening of it. We cannot currently tell which of these is true, but notice that all of them place a certain weight on the present moment, and there is something oddly steadying in the silence itself. For 70 years we have listened carefully and heard nothing. That could mean the galaxy is empty. It could mean we have searched a hot tub's worth of ocean. It could mean everyone else is quietly listening too, wondering the same thing. Whatever the reason, we know we are here. That much is certain, and it is not a small thing. On at least one world out of hundreds of billions, matter arranged itself into something that could look up and ask where everyone was. The question may go unanswered for a very long time, but somebody is asking it. In a silent galaxy, that alone is remarkable. We drift homeward now, back down through the spiral arms, past the quiet stars and their quiet planets, toward one small blue world that has been broadcasting the presence of life in its atmosphere for 2 billion years without ever meaning to. Below you, the Earth turns. Radio dishes point at the sky, listening patiently as they have every night for decades. Somewhere a survey is running right now, cataloging frequencies, finding nothing. There is no urgency in any of this. The signal, if it ever comes, will have been traveling for centuries before it arrives, and it will not mind waiting one more night. Close your eyes now. Let the question sit where it is, unanswered and unhurried. The galaxy has kept its silence for 13 billion years. It can keep it until morning. Mission complete, astronaut. The stars will wait for you. Good night.